Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going to Chapter 3.1, Matrix Sums and Products. In Chapter 3.1, we introduce arrays of numbers called matrices. Matrices are sometimes used to represent and manipulate large amounts of data efficiently, such as in digital image processing. Another application of matrices is to solve systems of linear equations. This will be the motivation for our discussion of matrices and matrix algebra. You most likely have already been exposed to matrices in a previous algebra class. Thus, our look at Chapter 3.1 will be to review and reinforce some of those ideas that you will have already seen. Let's get started by looking at some definitions. A matrix is a rectangular array of elements or entries, we also call them, arranged in rows and columns. We will start out with the entries being numbers. Sometimes we will find it useful to discuss specific entries in our matrix. And so we will talk about the entry that's in the A sub I j position. This will be the value in the ith row and jth column. For example, this is the entry in the A21 position because it's in the second row, first column. This would be the entry in the A12 position because it's in the first row, second column. Next, the order of a matrix describes its size by telling us how many rows and how many columns the matrix has. The matrix above has order m by m, read as m by n because it has m rows and n columns. A matrix can also be described by terms like square matrix. A matrix is square if it has n rows and n columns, in which case its order is n by n. It has the same number of rows and columns. It can be called a row vector or a column vector if all the entries are in a single row or a single column. So here we'll call this one a row vector. This one we'll call a column vector. Notice that when I talk about a row or column vector, we will sometimes put this arrow above the vector's name to signify that we're talking about a row or column vector specifically. Our textbook also uses lowercase letters for vectors and uppercase letters for matrices. We can classify them as being a diagonal matrix. A diagonal matrix is a square matrix with zeros off of the main diagonal. So all the entries above this, well, this would be the main diagonal here. So we'll say all the entries either above the main diagonal and below the main diagonal will all be zeros. Sometimes we'll talk about a triangular matrix. A triangular matrix has zeros in either the above or below the main diagonal. So we'll refer to this first one here as an upper triangular. Oh, so it'll be an R. Upper triangular. And this one would be a lower triangular. Other special matrices that we talk about are the zero matrix. A zero matrix is a matrix of all zeros. Or we also talk about the identity matrix. Sometimes the identity matrix is denoted I sub n, or just I. It is always going to be a square matrix. It'll be diagonal, with all the diagonal entries equal to 1. Here is an example of 3 different identity matrices. Maybe starting at the end, we could call this I2 to say that it's a 2 by 2 identity matrix, but commonly we just call it I, and we recognize the order is 2 by 2. Similarly, this one could be called I3 to recognize that it's a 3 by 3 identity matrix, but commonly we just refer to it as I without giving the lower index here. In general, an n by n identity matrix, we must have just the ones down this main diagonal, but zeros everywhere else. Let us look at some matrix computations that we should be familiar with. Matrix addition and subtraction. 2 matrices of the same order, so the same size, can only be added or subtracted by adding or subtracting the corresponding entries. Let's look at this example. Consider the sum of matrix A plus B. If we're going to add matrices A and B together, we want to do it in the most natural sense. And so we want to add their corresponding entries. So maybe add 1 and -3 together to get -2. 3 and 1 together to get 4. -2 and 0. 0 and 2. -1 and 3. 4 and 1 gives 5. So this would be the sum of matrices A and B. We could also subtract our matrices by subtracting corresponding entries. So 1 minus the -3. Be careful of a sign error here. We're subtracting the negative 3. 3 minus 1. Negative 2 minus 0. 0 minus 2. Negative 1 minus 3. 4 minus 1. I'm not sure why I decided to break this up into an intermediate step, but let's simplify this and say it's going to be the matrix entries 4, 2, negative 2, negative 2, negative 4, and 3. Matrix A plus matrix C. Here, little hairs on the back of your neck should stand up, telling you that you cannot do this. Say this matrix sum is not defined. So maybe you should identify here that matrix A is a 3 by 2 matrix because it has 3 rows and 2 columns, while matrix B is a 2 by 2 matrix, 2 rows and 2 columns. And maybe identify here that the matrices are not the same size. So they cannot be added together. Let's move on and talk about scalar multiplication. To find the product of a matrix and a real number, we will refer to a real number usually as a scalar. We multiply each entry in the matrix by the number. So when we scale a matrix by the value k, distribute the k to every value in the matrix. So let's find the following. If A is this 3 by 2 matrix, and get used to thinking about the size of matrices, 3 rows, 2 columns, then what would 3 times A be? So multiply each entry by 3. This would be 3A. Okay, I'd like to give you a moment to do the next example on your own. Find the matrix 2A minus B. Now I'd like you to pause the video for a moment and come up with this new matrix 2A times B. After you're done, come back and let's verify that we get the same thing. I'll see you in a moment. Okay, let's see how you did. To find the matrix 2A minus B, and I want to show my work, so I'm going to do it with an intermediate step. I'm first going to figure out what is the matrix 2A. So I'll scale the matrix A by 2. And then now we'll figure out what is the matrix created by looking at 2a minus b. So 2a minus b is going to be 2 minus the negative 3. I think that's going to be a 5. 6 minus 1. Negative 4 minus 0. 0 minus 2. Negative 2 minus 3. 8 minus 1. I hope this is the 3 by 2 matrix that you created. Okay. We can also look at matrix multiplication. Ooh, that's a weird way to write that. 2 matrix product. I should have said, well, I don't know why I wrote the word 2 there. This should say the matrix product. Or the product of an M by R matrix A and an R by N matrix B is another matrix C that's M by N. Now, there's a lot of letters running around here. Let's make sure this makes sense. What I'm trying to say is that we can only multiply matrices if the inner dimensions agree. So here again, matrix A is M by R. Matrix B was R by N. Notice that the inside dimensions agree. They're both R. This is what tells you that you're allowed to do the multiplication. Then the outside dimensions, these are what tells you the size of the product. That matrix C will be an M by N matrix when we're done. For example, if matrix A is a 3 by 2 matrix and matrix B is a 2 by 2 matrix, then matrix C will have to be a 3 by 2. Here I'm asking you to notice that because the inner dimensions are the same, we're allowed to do the matrix multiplication. The outer dimensions, these will tell you the size of our product. We know C will have to be a 3 by 2 matrix. How do we actually come up with this matrix C? So one way to look at this is to first maybe identify that you're looking for specific entries in your matrix. For example, this entry here is referred to as your C11 entry because it's in the first row and the first column. And the way you come up with the C11 entry is you multiply the entries in the first row of A times the entries in the first column of B, adding them up as you go. So you'll have the value 2 times 1 plus the value 1 times negative 1. And this should come out to be 1. And that's why this entry here is a 1. If you wanted to find the entry that was in the C12 position, first row, second column, then looking at our two matrices A and B, you would take the first row of A times the second column of B, adding up these products as you go. So it would be 2 times 2 plus 1 times 3, which gives you the value 7 that's in the C12 position. If we were to continue, we should get the matrix product here. You should confirm all of these values are correct. But just for giggles, let's just check one more just to make sure we understand this process. If I wanted to verify why this value is -3, you could say this is in the C22 position. So you would take the values in the second row of A times the values in the second column of B. So C22 would be 2 times 2 plus, oh, I'm looking at the row. I didn't look at the second row. I looked at the first row. I got to look here. Second row, second column. Let me try that again. It would be 0 times 2 plus -1 times 3, which should give us -3. Let's do one more since I almost made an error with that. Let's look at the value -2. How did this value come about? Well, this would be the value that's in the C31 position. Third row, first column. So to verify how this entry is obtained, we'll take the third row of A times the values in the first column of B. So it would be 1 times 1. So this entry times this entry plus 3 times -1. Which should be 1 minus 3 or -2. Okay, I hope this makes sense because I'd like to practice this skill now. Find the following if matrices A, B, C, and D are defined as these matrices. Now, I'd like you to pause the video and work on these. Let's do them one at a time just to make sure that we're comfortable with matrix multiplication. So if you could pause the video for just a moment, I'd like you to find the product of matrices A and B. I'll see you back here in just a moment after you work on that. Okay, I hope you looked at the products matrices A and B. Let's see how we did. And I'm going to rewrite the matrices here just so I can organize my work. So here you'd first like to identify that matrix A is a 2 by 2 matrix. Matrix B is a 2 by 2 matrix. Because the inner dimensions agree, we're allowed to do the multiplication. The outer dimensions, remember these ones tell us the size of our product. So we know when we multiply this together, we're going to come up with another matrix that must also be a 2 by 2 matrix. And now for this example, I'd like to identify the entries again, just to help you with the matrix multiplication. Maybe you could say this is the C11 position, first row, first column. C1, 2 position, first row, second column. C2, 1 position, second row, first column. C2, 2 position, second row, second column. So if you're looking for the value that's in the 1, 1 position, take the first row of A and the first column of B. And generally I'll do this multiplication in my head. It'd be 1 times negative 2 is negative 2 plus 2 times 4, which is 8. So, for this example, since I'm discussing it with you, I'm going to write out my work as I go. But like I said, I typically do this in my head. So this is going to be 1 times negative 2 plus 2 times 4. If I get this right, I think this should be 6. One times negative 2 is negative 2. 2 times 4 is 8. Okay, let's continue. If I wanted to find the value in the C1, 2 position, then I would take the values that are in matrix A, that are in the first row, and multiply the values that are in matrix B in the second column. First row, second column. So if I do this carefully, I think it should be 1 times 1 plus 2 times 5. If I do this right, I believe it should be 11. The 2, 1 position. We'll take the values in the second row of A times the values in the first column of B. So I believe it should be 0 times negative 2 plus 3 times 4. And I believe this should be 12. Last one, C2, 2 position. We'll take the values in the second row of A times the values in the second column of B. So I believe this should look like 0 times 1 plus 3 times 5. And if you're following along, double check I'm right, but I believe this is 15. Now again, typically I do not show this step here. Once you do enough matrix multiplication, you probably just do these computations in your head. Or maybe with the use of a calculator. Okay, let's do another one. Let's look at the product of A times C. Again, I'd like to ask you to pause the video and work out this matrix multiplication on your own, and then come back and let's verify that we get the same answer. I'll see you in a moment. Okay, let's see how you did with the product of matrices A and C. And again, I'd like to rewrite them here just so it makes my work easy to follow. So matrix A, matrix C, Now, the first thing I want to think about is this matrix multiplication defined? So here you're probably noticing A is a 2 by 2 matrix. C is a 2 by 3 matrix, 2 rows, 3 columns. And again, because the matrix inner products are agree, this tells me I'm allowed to do the multiplication. And the outer dimensions will tell me the size of the product. So I know when I multiply this together, I'm going to get back a 2 by 3 matrix. So 2 rows, 3 columns. So now the way I typically do this, first row of A times the first column of B, I think it's going to be 1 plus 4 should be a 5. First row of A, second column of B should be 0 plus 2 is 2. First row of A, third column of B should be 1 plus 6 is 7. Second row of A, first column of B is going to be 0 plus 6, 0 plus 3, 0 plus 9. It should look like that. Now, in the past, a lot of students have asked me, can we do this on our calculator? And I'm going to say the answer is yes. I believe this to be a low-level skill, just like multiplication of regular numbers or division of regular numbers that we are all familiar with already. If you have a calculator that does matrix multiplication, you are welcome to use it, but you are not required to use a calculator for this. Now, if you have a calculator, if like one like mine, a TI-84, which a lot of us do, even if you have a different brand of calculator, you may have to YouTube to figure out how to do matrix multiplications. But if you have a calculator that does it, feel free and use it for these computations. So if I'm going to use my calculator, the first thing I need to do is enter the matrices A and C into the calculator. And you'll do that using the matrix button here. It's underneath the math key. Now in my matrix key, notice that it's blue, so I'm going to hit the second and then hit the matrix or the x to the -1 key. And the first thing I want to do is edit a matrix. So let's edit matrix A. Currently, it says it's a 3 by 3 matrix. I'm going to turn it into a 2 by 2 matrix. So, and let's enter in our values. 1, 2, 0, 3. Double check and make sure you entered your values correctly. Now let's enter the matrix C. So go back into second, matrix to get to your menu, arrow over to edit, and now let's change matrix C. Now I could put this in matrix B, but just to keep my labeling consistent, I'm going to put it in matrix C. And I want matrix C to be a 2 by 3 matrix, which it is. So enter the values. Okay, verify that you have the correct numbers in your matrix. And then now let's get back out of this and go back to our home screen. Now there's different ways you can do this. You do not have to do it like I'm doing it. There are definitely shortcuts. But just to verify you're doing the right multiplication, I'm going to go and grab my first matrix, matrix A, multiply it by matrix B. No, not matrix B. We did matrix C. which was number 3. And this should confirm our product of our 2 by 3 matrix. And it looks like we did it right. Okay, let's move on. Let's try another one. Let's look at the product of matrix A and I. So just to keep this clear, I want to, and show my work nicely, I'm going to recopy these matrices down. Here's matrix A. And now matrix I. Recall we said that matrix I, also referred to as the identity matrix. Is a square matrix. It's a diagonal matrix with entries only on the main diagonal that are all ones. So it would have to look like 1, 1, 0, 0. Now to do our matrix multiplication, again, notice that this is a 2 by 2 matrix times another 2 by 2 matrix. So we're allowed to do this multiplication. And we should expect the product should also be a 2 by 2 matrix. It should have entries 1 times 1 is 1, plus 2 times 0. So just 1. Your next value would be 1 times 0 is 0, plus 2 times 1 should be a 2. Next one, 0 times 1 plus 3 times 0 should be 0. Last one, 0 times 0 plus 3 times 3 is 3. Notice that the matrix we got back is the exact same as the matrix A that we started with. And so what you'd like to know is anytime you multiply by the identity matrix, think of this as the 1 of matrices. Something times 1 is always itself. Or to put it another way, any matrix A times I is always going to equal matrix A. Okay, we have one more example, matrix C times matrix D. Again, I'd like you to be able to work this on your own. So if you could take a minute and find this matrix product C times D. After you're done with your matrix product, come back and let's verify that we get the same result here. I'll see you in a moment. Okay, let's see how we do with this matrix multiplication. Again, just so we get used to the terminology, I want you to verify that this matrix multiplication is defined. This is a 2 by 3 matrix C, 2 rows, 3 columns. Matrix D is a 3 by 1 matrix, 3 rows, 1 column. Our inner dimensions agree. This tells me I'm allowed to do the multiplication. The outer dimensions tell me the size of the product. So we're expecting to get back a 2 by 1 matrix. 2 rows, 1 column. So our 2 rows, 1 column would be our first row times the first column. If I do this right, it'd be 1 times negative 2, 0 times 1, 1 times 3. I think that's going to be negative 2 plus 3 I believe this is going to be a 1. Okay. The second value in our product will be 2 times -2 is -4, plus 1 is -3, plus 9. I believe this should be the value 6. Now, I could have done this matrix multiplication on the calculator, yes, but generally for small matrices, I do these by hand. I'd also like to show you an alternate method here. Whenever I do a matrix multiplication where the second matrix is a column vector, an alternate way of doing this would be rewriting this as -2 times the first column of the matrix C plus 1 times the second column of the matrix C plus 3 times the last column of the matrix C. Sometimes we refer to this as a linear combination of the columns of C, because we're doing -2 of the first column of C, and then we're doing 1 of the second column, and then we're going to do 3 of this last column. So here I'll say this is going to be -2 plus 0 plus 3 still gives me the value 1. -2 is, this would be -4 plus 1 is -3 plus 9 gives us 6. So I've shown you now maybe 3 ways you could have done this matrix multiplication. Using your traditional entry by entry approach, using your calculator, or using this alternate method. Okay, let's move on. Systems of equations. The focus of our class will be to use matrices to solve systems of linear equations. Again, this is a topic that you should remember seeing from maybe your Math 1010 intermediate algebra class and even Math 1050. And at that time, we looked at maybe a couple of simple systems of equations. Some of them got more complicated, as I recall, though. But a typical system of equations might look like this. And our goal is to find a solution. And for us, a solution will be an ordered pair, x comma y, that satisfy both equations at the same time. Now, in Math 10 and 1050, 1010 and 1050, we looked at several methods for solving such systems. The graphical method. Here you probably remember the graphical method in general, not necessarily for these 2 equations I'd give you, but in general, the graphical method says graph your first linear equation, graph your second linear equation. Where these 2 equations or lines intersect, this will be the solution. X comma y. We will not be using a graphical approach when solving these systems. Algebraic approaches that you should recall were the substitution method and the elimination method. However, other methods that you probably recall from Math 1050 were referred to as matrix methods, and there were several that we talked about. And so I'm going to talk about several in our class as well. These will be spanned out over several chapters, from chapters 3.2 through chapters 3.4. We'll look at matrix methods. However, just for fun, let's solve this system of equation using the elimination method. I have a reason for wanting to do this, so not just to practice skills we've already seen. Now recall with the elimination method, you want to add these two equations together. And so for that reason, it's sometimes also referred to as the addition method. However, to use the addition method, when you add these equations together, you want them to have one of the variables cancel. It doesn't matter which variable you cancel. You can make the x variable cancel, or you can make the y variable cancel. It does not matter. I'm going to choose to make the x variable cancel here. So what I'm going to do is take my original equation, the x plus 2y equals 7. And I'm going to choose to multiply everything in this first equation by a value that'll make it cancel, have the x's cancel. What I'm trying to get to is I'm going to multiply this first equation by -2 on both sides. However, when I do this multiplication, the second equation doesn't change. So this is my original second equation. Notice that multiplying the first equation by -2 does not change the second equation. So when we do this multiplication, don't forget you must distribute that -2 to both entries in the parentheses, both terms here. So we should get -2x plus 4y equals -14. The second equation stayed the same. And now we would like to add these two equations together. Notice when you add them together, the x variables being opposite in sign but the same number, these will cancel. And so we get 1y, or just y, equals 3. This is half of our solution. We still have to find x. Now, it doesn't matter which of these two equations you use to find x. Remember, both equations will cross at the same point. So it doesn't matter. They both have the same x value when y is 3. But I'm going to choose the easier of the two equations, the one that had the x plus 2y equals 7. And here we know y is really going to be 3. I believe this tells us x is going to equal 1. So here, our solution will be the ordered pair 1, 3. This will be the value that satisfies both equations simultaneously. Now, there's a reason that I wanted to practice these skills with you. We'll see this come up again in chapter 3.2. Now, in chapter 3.2, we're going to be focusing on matrix methods. And this also ties in with the skills we practiced today, matrix multiplication. To use matrix methods, we first need to write the system of equations as a matrix equation of the form AX equals B. this is where we'll stop for chapter 3.1, and in chapter 3.2 we'll start to develop different matrix methods for solving systems of the form AX equals B. But let's do that here just so we can practice it. And for clarity, I'm gonna rewrite my original system here for us. So it's x plus 2y equals 7. 2x plus 5y equals 17. And I want to write it in the form AX equals B. Now, the way I do this is the matrix A, this is sometimes referred to as your coefficient matrix. And then we'll multiply this times the vector x, and notice this is going to be a column vector. And this is going to have to equal a matrix B. And again, notice the notation. This will also be a column vector. Now, my coefficient matrix is just going to be the coefficients of our system of equations on the left side. It's going to be the 1, 2, 2, 5. So this is a nice 2 by 2 matrix. 2 rows, 2 columns. The vector x is going to be the vector of variables, just the x and the y variables. And the vector b is going to be the right-hand side of our system of equations, so just 7 and 17. Now, we probably should confirm that the left-hand side of our matrix equation does equal the left-hand side of our original system. So here, notice that this is going to be a 2 by 2 matrix times a 2 by 1 matrix. The inner dimensions are the same, so we allow to do the multiplication. And when we do this multiplication, it'll be 1 times 2, or 1 and 2, times xy, or specifically it's 1 times x plus 2 times y. It's this first part of our system of equations. And this has to equal 7. The second part, this will be the values 2 times 5 times x and y. So it'll be 2 times x plus 5 times y, and this has to equal the right-hand side, 17. So now we can say this matrix is, or the system of equations is in a matrix equation form. AX equals B. And this is where we're going to be starting in chapter 3.2. So I'm going to stop this video here. It was nice working with you today, and I'll see you in our next video.